Hi, hello everyone. This is Hemalatha from Marri Laxman Reddy Institute of Technology and Management. After a small gap, today I'm going to explain you about dielectrics and magnetic materials, which is the third unit in applied physics. So basically nowadays every college is going for NBA. So the basic thing what they are asking is, what is the course outcome of your particular topic? So as I'm going with the dielectrics and magnetic materials, the CO, that is a course outcome which the student will be gaining after completing this unit, that is this module, that is understand the properties of dielectric and magnetic materials and their applicability in engineering contexts. So he has to study, as he already know what is a dielectric and what are magnetic materials. So here he will be utilizing those materials and he will be applying these materials in some engineering application context. That is what the outcome he is going to gain in this particular topic or module. So let us start. Basically, what is a dielectric? What is the basic definition of a dielectric? Now, the definition of dielectric is nothing but, for example, we take an atom. An atom consists of electrons and a nucleus. Now, the electrons are revolving around the nucleus. That means these electrons, they are attached to their nucleus. That attachment forms you a dielectric material. So, as far as the definition is considered, what we say is, all dielectrics are electrical insulators and they mainly use it to store electrical energy. They are acting like insulators. That means the example which I took, the atom consisting of nucleus and electrons are revolving. That means the electrons are attached to that nucleus. They does not allow other electrons from other atoms to enter and revolve around their parent nucleus. That means as they are revolving around the nucleus, they store the energy which is in form of electrical energy. So we generally say that dielectrics are nothing but insulating materials. They will be used as insulating materials in between the two plates of a parallel plate capacitor or in any of the materials to make them not to be in contact with each other. We place this material which is called as a dielectric material. So that is the major definition of a dielectric material. The examples are mica. Mica is one of the best example of a dielectric material, or in general, to make you understand more familiar, you are constructing a wall. In the construction of a wall, we are using bricks. Once, to bind one brick with the other brick, we are using cement material. So here, the cement is acting as a binding material between the two bricks. So we call this cement as a dielectric material. So here, that is one of the example where I can make you understand what a dielectric material exactly is. But the general examples of dielectric are mica, glass, plastic, water, and polar molecules. These are the best examples of dielectric materials. Now, dielectric materials, to go deep into the subject of dielectric materials, one should know the basic definition, that is, what is a dipole or how a dipole formation takes place. Now, as I told, we are taking an atom. In an atom, it is having a positive charge that is called as a nucleus, and electrons are present which possess negative charge. Now, if with respect to the applied field, I am applying some force, I call it as a field. Now, I use the word field instead of force. Now, I am applying some field on that particular atom. Then automatically the charge carriers which are present inside the atom gets disturbed. Now, whatever the disturbance which is created with respect to a certain distance, that is called as a dipole. So, here we say dipole is nothing but distribution of charge carriers, movement of charge carriers with respect to certain distance. It is called as a dipole. I hope everyone understood. We are taking a positive charge and negative charge. On that positive and negative charge, we are applying some field. Then automatically positive charge moves in one direction, negative charge moves in other direction. Now there is some distance which is created between these two charge carriers. Now that distance with respect to the movement of charge carriers forms you a dipole. Okay? That is the first thing. Second thing is, once dipoles are formed in an atom or in a molecule, they give rise to the next component which is called as the dipole moment. What is first thing? It is dipole. How is a dipole formed? If the charge carriers are being separated with a certain distance with respect to the applied field, then a dipole formation takes place. Now, we are considering an atom or we are considering a molecule in which dipole formation has taken place. Now, the dipoles which are formed with respect to the applied field, they produce dipole moment. That dipole moment we generally represent it by the letter mu. Dipole moment we represent it by the letter mu. Now, what is this dipole moment? Dipole moment is defined as the product of charge carriers Q1, Q2 multiplied with the distance. Distance of separation is taking place if the charge carriers are getting separated. So, the product of these two charge carriers multiplied with that distance, we call it as the dipole moment, which is represented by the letter mu. Now, in this PPT, as I have shown you, it has Q. Q is nothing but Q1 plus Q2. I have taken it as Q is nothing but Q1 plus Q2. So, I wrote it as mu is equal to Q into D. D is nothing but the distance. You can represent it by the letter R or you can represent it by the letter D. So, now we define the dipole moment as the product of magnitude of either of the charges and the separation between them is called as a dipole moment, which is represented by the letter mu. Mu is equal to Q into D, and the units of dipole moment are Coulomb meter. The units of dipole moment are Coulomb meter. So, the first definition is dipole, second definition is dipole moment. Now, the next definition, some of the important terms which everyone should remember in this dielectric materials is what is meant by electric intensity or electric field strength. Generally, we represent it by the letter capital E. Now, for example, you are having an atom. Charges are moving with respect to the applied field. Then, the amount of force which is acting per unit charge, the amount of force which is acting on the unit charge per unit charge, that is represented as the electric field strength E. E is equal to F by dq. What is F? The field which you are applying is making the charge carriers move from one position to other position. So, how much amount of force is produced per unit charge? That is called as the electric field strength or electric intensity, which we are representing it by the letter E. Next important thing is what is meant by permittivity. In order to define what is called as dielectric constant, we need to define what is meant by permittivity. Now, permittivity, it is a measure of resistance that is encountered when forming an electric field in a medium. Now, we have taken the atom, you are applying electric field. Once when you apply electric field on an atom, then the electron starts their motion. That means the movement of charge carriers is taking place. So, how much resistance is possessed by the electrons inside the medium, that is called as permittivity. Or in simple words, we can define permittivity. It is a measure of how much an electric field is affected by the dielectric medium. Now, next, what is meant by permittivity of medium and permittivity of free space? Because generally we represent the dielectric constant by epsilon r. To define these two, we should know what is meant by permittivity of the medium and we should know what is meant by permittivity of free space, which we represented by the letters epsilon and epsilon naught. Now, first, permittivity of the medium. How much amount of electric field is generated per unit charge inside that medium is is represented as the permittivity of the medium epsilon. Now, epsilon naught, the electric field generated in vacuum, that we are measuring the amount of charge carriers per unit electric field, which we are calling it as the permittivity of the medium. Now, next is epsilon naught, that is permittivity of free space. That is nothing but the field which is generated in vacuum, and we represent it by epsilon naught, and it has a constant or a fixed value, that is 8.85 into 10 power minus 12 farad per meter. Now, let us define what is meant by dielectric constant. Once a student is familiar with epsilon and epsilon naught, now he is ready to define what is meant by dielectric constant, which we are representing it by the letter epsilon r. Now, it is defined as the ratio of permittivity of the medium to that of permittivity of free space. That is, epsilon r is equal to epsilon by epsilon naught. So, epsilon r, which is called as a dielectric constant, it is defined as a ratio of permittivity of the medium to permittivity of free space. Now, epsilon r, dielectric constant, does not have any units. Why it does not have any units? Because it is the ratio of permittivity of medium and the ratio of permittivity of free space. So, both the numerator and denominator are permittivities, so it does not carry any units. Now, this is one of the important definition with respect to dielectric materials, that is a dielectric constant. Now, next let us define the dipole moment is completed. Next, let us define the other important term, that is polarization or electric polarization. Now, what is meant by polarization? Polarization means we are applying electric field on the atom, then automatically the charge carriers are moving. That means there is a separation created between the charge carriers. Once the separation is created between the charge carriers, then polarization will take place. Polarization means dipole formation is taking place. This dipole formation is giving rise to dipole moment. Now, the ultimate dipole moment which is produced per unit volume or per unit electric field is defined as polarization. Now, that means what we say is we generally represent the electric field strength by E, and then we represent the dipole moment by mu. That is, the amount of electric field which you are producing, which you are applying, will give rise to the amount of the dipole moment which is produced. That means both are direct proportional to each other. E is proportional to mu. Then remove this proportionality constant, introduce a constant called as alpha, alpha into mu. Now, what is this alpha? Alpha is called as polarization constant. Now, from this I can define polarization as alpha is equal to, now here let us take this equation, not in this way, let us take in this form, a small mistake here. Now, mu is proportional to E. Mu is proportional to E. Mu is equal to alpha E. Now, define polarization as alpha is equal to mu by E. Now, I hope what is mu everyone knows. Mu is nothing but the dipole moment. Now, what is this E? E is nothing but the applied field, that is the electric field. Now, we can define polarization as dipole moment per unit electric field. Dipole moment per unit electric field, that is called as polarization. Or here I have represented it as P. P is called as polarization. Here I have represented it as alpha. Both are one and the same. So, P is proportional to E. P is equal to alpha E. This polarization P, alpha E, it is called as a polarization constant. So, alpha is equal to P by E, you can write. P is nothing but the dipole moment mu by E. So, the units of polarization is farad meter square. The units of polarization are farad meter square. So, now we have come across four definitions. First one is dipole. Second one is dipole moment. Third one is we have come across the dielectric constant epsilon r. Fourth one is polarization. These are the four major definitions which has to be covered, which a student need to understand in this concept. Now, next, Electric susceptibility, another important definition. Now, susceptibility does not have a perfect definition. Generally, we define it in terms of a property. It is a property of a material. It does not carry a particular definition. The polarization vector P is proportional to total electric flux density in the direction of the electric field. That is, we have written previously, P is proportional to E. P is polarization, E is the applied field. P is proportional to E. Let us remove this proportionality constant and introduce another constant which is called as epsilon. P is equal to A epsilon naught E epsilon naught. Now, introduce here itself psi E. We can write the polarization vector which is represented as P is equal to E epsilon naught into psi E. Now, what is this psi E called as? Psi E is called as electric susceptibility. So, as I told you, it does not carry any particular definition. It is a property, measurable value. So, psi is equal to P by E epsilon naught. So, that is equal to, already there is one small derivation, that is polarization with respect to polarization relation. We have E is equal to E epsilon naught into epsilon r minus 1. Now, for this sake, let us take this equation. So, polarization, we are writing it as E epsilon naught into epsilon r minus 1 by E epsilon naught. Now, you can cancel these two. Then you are left with, as this E and E also gets cancelled, you are left with psi E is equal to epsilon r minus 1. This is just a measuring property. There is no particular definition for this one. Susceptibility psi E. Okay, this is one more definition. Next, come to, these are the 5 definitions which I have come across: dipole, dipole moment, dielectric constant, polarization, then susceptibility. So, these 5 definitions every student should remember, and these are more important. Okay, next come to the types of polarization process. Based on the amount of electric field, you are applying on an atom, 4 different types of polarization process are taking place. First one is called as electronic polarization, which we represented by the letter alpha E. Because we are representing polarization by alpha, so electronic polarization is represented by alpha E. Second polarization, ionic polarization, we are representing it by the letter alpha I. Third polarization is orientation polarization, which is represented by alpha naught. This is also called as dipolar polarization also. Orientation polarization, other words, also called as dipolar polarization, which is represented by alpha naught. Now, last polarization is space charge polarization. We represent it by alpha S. Now, for an atom, when you are applying electric field, 4 different types of polarizations are taking place. So, the total polarization which is taking place is given by alpha E plus alpha I plus alpha naught plus alpha S. So, this is the total polarization which occurs in a dielectric material. Okay. Now, let us explain. Let us define these definitions. What is meant by electronic polarization, ionic, orientation, space charge. To make you better understand, I have given one figure here. Now, see this first figure. Let us go with respect to no field. That means we are not applying any field on the atom. Now, when you are not applying any field on the atom, let us take a nucleus is present in an atom. Electrons are revolving around the nucleus. Okay, this is the first situation. Now, when you are applying the field, we are applying electric field in opposite direction. Then what is happening when you are applying electric field on this situation? Then automatically this charge carrier moves here. That is, here initially this was present here. Now there is a change in its position. Now the charge carriers are moving in this direction. That is, we define electronic polarization as, with respect to the applied field, displacement of positively charged particle and negatively charged particle in opposite direction. See, this positive charged particle is moving in this direction, negative charged particle is moving in this direction. With respect to the applied field, the displacement whatever is produced with respect to the applied field, that displacement we are calling it as electronic polarization. So once again I am defining electronic polarization: displacement of positively charged particle and a negatively charged particle in opposite directions with respect to the applied field. That is called as electronic polarization, which we are representing it by the letter alpha E. Okay. Now, next, second polarization is, now one more thing, this occurs, this type of polarization takes place in all types of materials. This type of polarization occurs in all types of materials. Then, second, ionic polarization, which we are representing it by alpha I. Ionic, ions. This is explained based on ions. As you already know, cation, anion are present in an atom. Now, we are having one atom in which cation and anion is present. Now, without applying the field, this is the situation. Now, when you are applying the field, automatically the displacement of charge carriers is taking place with respect to the field in opposite directions. Here, we have not shown, but this is how the displacement of charge carriers takes place. That is, the displacement of positive cation and anion in opposite directions with respect to the applied field. That is defined as ionic polarization. And one speciality of this ionic polarization is it occurs only in ionic solids. It takes place only in ionic solids. Other solids, it does not take place. Covalent solids or any other solids, it does not take place. It takes place only in ionic solids. That is alpha I. Now, third one, that is dipolar polarization or orientation polarization. Now, first I give the definition, then I'll show you the figure. In general, the movement of electrons in any atom will be like this. This is how randomly they move. When you apply field, then automatically the charge carriers align themselves, along the direction of the applied field. See, this is the direction of the applied field. All the charge carriers, they try to align along the direction of the applied field. That type of polarization is called as dipolar polarization or orientation polarization, which is represented by alpha naught. Okay. This type of polarization, what will happen is, when you apply electric field, all the randomly oriented charge carriers, they try themselves to align along the direction of the applied field. That type of polarization is called as orientation polarization. And one speciality of this polarization is there will be permanent dipoles will be formed in case of this type of polarization. Now, permanent dipoles means this takes place only in polar molecules. No other molecules, this type of polarization takes place only in polar molecules, because water is the best example of a polar molecule. Now, in order to form water molecule, what we are taking, hydrogen and oxygen, we are combining these two and we are forming a water molecule. Now, the person will ask, I want my hydrogen back, I want my oxygen back. Is it possible to separate these two atoms? No. So, such type of molecules are called as polar molecules. And in polar molecules, permanent dipoles will be formed. That means the orientation of these atoms, the electrons or the charge carriers, once they orient, then you cannot disturb the orientation. That type of molecules or that type of polarization is called as dipolar polarization. Next, space charge polarization. What is a space charge? Now, in general, in any type of a material, here the alignment of charge carriers will be like this. This is how. One positive charge, negative charge, positive charge, negative charge. Now, I apply electric field on this type of situation in general. Now, what will happen with respect to the applied field is, all the similar type of charge carriers will try to align themselves along one side, other charge carriers on the surface of this structure. On the surface of the structure, all the same type of charge carriers would get aligned. This type of polarization, we call it as space charge polarization. And in general, in dielectric materials, we consider these two types of polarizations. This is a neglected type of polarization, because this type of polarization generally will come in defects which occurs in crystals. So here we are not concerned with the defects. So that's why we are going with respect to electronic, ionic and orientation polarization. So in the next class, I will tell you about the brief introduction about electronic polarization, ionic polarization, orientation polarization, and the other concepts which are related to this one. With this, I end here, and the type reference book which I have used for this topic is SO Pillai textbook. Okay, thank you.